Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to discuss about the module Ion Implantation from the paper Semiconductor Materials and Devices. So students, let us see what we are going to learn in this module. First, the characteristics of ion implantation will be discussed. Second, the expression for penetration range will be discussed in this module. Third, the nuclear and electronic stopping will be discussed in detail. So students, let us start with a basic introduction about the module. Ion implantation as applied to semiconductor technology is a process by which energetic impurity atoms can be introduced into a single crystal substrate in order to change its electronic properties. Implantation is ordinarily carried out with ion energies in the range of 50 to 500 kilo electron volt. Basic requirements for ion implantation systems are ion sources and means for their extraction, acceleration and purification. This is followed by beam deflection and scanning prior to the impingement to the substrate. Ion implantation provides an alternative to diffusion as a means for junction fabrication in semiconductor technology. There are some disadvantages to ion implantation as well. The equipment is highly sophisticated and expensive, so that the technology is at an economic disadvantage when compared to the diffusion. So in those areas where diffusion can be used. So the competitive disadvantage is worse for gallium arsenide, where energy requirements are in the range of 200 to 500 kilo electron volt, than for silicon, which has a range of 50 to 150 kilo electron volt range. This, however, is offset by the fact that this technique lends itself to a high degree of automation, including inline process monitoring as well as endpoint determination. As a result, ion implantation is extensively used in both technologies today. A second disadvantage is that an ion implantation results in the damage of semiconductor. Annealing at elevated temperatures is necessary to heal some of all this damage. This is not a problem with silicon, since its vapor pressure is extremely low at annealing temperatures. Furthermore, silicon is often subjected to later higher temperature processes where this damage can be completely annealed. With gallium arsenide, however, it is necessary to use a cap or to conduct the anneal in an arsenic overpressure in order to avoid disassociation and loss of stoichiometry. Neither approach is completely satisfactory, and this problem has not been solved at the present time. Characteristics of ion implantation. The technique, however, has many unique characteristics which have led to its rapid development from a research tool to an extremely flexible, competitive technology. So, some of these unique characteristics are now considered. First, mass separation techniques can be used to obtain a monoenergetic, highly pure beam of impurity atoms free from contamination. Thus, a single machine can be used for a wide variety of impurities. Furthermore, the process of implantation is carried out under high vacuum conditions, that is, in an inherently clean environment. Second, a wide range of doses from 10 to the power 11 to 10 to the power 17 ions per centimeter square can be delivered to the target and controlled to within plus minus 1% over this range. In contrast, control of impurity concentration in diffusion system is at best 5 to 10% at higher concentrations, and they become worse at low concentrations. Furthermore, dopant incorporation during diffusion is sensitive to variations in the electronic character of the surface, whereas this is not the case with ion implantation. Thus, ion implantation provides inherently more uniform surface coverage than does the diffusion, particularly when low surface concentrations are required and when the surface has a pattern of doped regions. So the third characteristics of ion implantation is it is usually carried out at room temperature. As a result, a wide variety of masks such as silica, silicon nitride, aluminium, and photoresist can be used for selective doping. So this gives great freedom in the design of unique self-aligned mask techniques for device fabrication which are not possible with diffusion technology. Fourth one is ion implantation provides independent control of dosage and penetration depth. Many types of dopant profiles can be obtained by controlling the energy and dosage of multiple implants of the same or different impurities. Both hyper-abrupt and retrograde doping profiles can be made with relative ease in this manner. Next is ion implantation is a non-equilibrium process, so that the resulting carrier concentration is not limited by thermodynamic considerations, but rather by the ability of the dopant to become electronically active in the host lattice. Thus, it is possible to introduce dopants into a semiconductor at concentrations in excess of their equilibrium solid solubility. The last one is that the ion implantation can also be used for depositing a controlled amount of charge species in a specific region of a semiconductor. Thus, it has important applications in the threshold control of MOS devices. Penetration range. There are two basic stopping mechanisms by which energetic ions upon entering a semiconductor can be brought to rest. The first of these is by energy transfer to the target nuclei. This causes deflection of the projectile ions and also a dislodging of the target nuclei from their original sites. So if E is the energy of the ion at any point x along its path, we can define a nuclear stopping power Sn, which is equal to 1 by n multiplied by dE by dxn to characterize this process. So nuclear stopping results in the physical damage to the semiconductor, which takes the form of point as well as line defects. Often the semiconductor can become amorphous or semi-insulating as a result of this process. A second stopping process is by the interaction of the ion with both bound and free electrons in the target. So students, this gives rise to the transient generation of whole electron pairs as energy is lost by the moving ion. So we can define an electronic stopping power SE to be equal to 1 by n multiplied by dE by dxE to characterize this process. So the average rate of energy loss with distance is given by minus dE by dx equal to n multiplied by Sne plus See, where n is the density of target atoms in the semiconductor. If the total distance traveled by the ion before coming to rest is capital R, then capital R equal to integral 0 to capital R dx equal to 1 by n multiplied by 0 to E naught dE by Sne plus See, where E naught is the initial ion energy. The quantity R is known as the range. So a more significant parameter of interest in semiconductor technology is the projection of this range along the direction of the incident ion, which is shown in this figure. Because of the statistical nature of this process, this projected range is characterized by its mean value Rp as well as by a standard deviation delta Rp along the direction of the incident ion. Thus, latter term is referred to as the straggle. In practice, the ion beam also has a spread at right angles to its incident, which is shown in this figure. So this transverse straggle is denoted by delta RT and is of importance in determining the doping distribution near the edge of a window, which is cut in a mask. So transverse straggle can be ignored if the width of this window is large compared to the implant depth. For this case, the statistical distribution for an amorphous target can be described by a one-dimensional Gaussian distribution function of the form phi x equal to exponential minus half x minus x bar by sigma the whole square, where x bar is the mean value and sigma is the standard deviation. So integration of this function over the limit plus minus infinity results in the dose. So writing this dose as Q naught ions per centimeter square and noting that integral 0 to infinity e to the power minus z square dz equal to root of pi by 2. So the impurity distribution is given by Nx equal to Q naught by root of 2 pi multiplied by delta Rp multiplied by exponential of minus half x minus Rp by delta Rp the whole square. This function has a maximum at Rp and falls off rapidly on either side of this mean value. So in a single crystal semiconductors, if the incident beam is aligned to a major crystallographic axis, the ions can be steered for a considerable distance through the lattice with little energy loss by a process known as channeling. Such channeled beams results in greatly increased penetration depth as well as in reduced lattice order. Unfortunately, the range is now critically dependent on the degree of alignment or misalignment of the beam and the crystallographic axis and also on the ion dosing. The formation of a tail in the doping profile can also be caused by a rapid interstitial diffusion process undergone by the particles once they have lost their incident energy. Such particles continue diffusing even at room temperature until they encounter suitable trapping centers such as vacancies or a surface. So if tau is an average trapping time and d is the diffusion coefficient associated with this process, it can be shown that the impurity tail will be of the form which is given by n equal to n naught exponential minus x by root of d tau. In some situations, this tail region is enhanced when the semiconductor is annealed by heat treatment after the implantation. However, tau can be very short in heavily damaged material, thus suppressing its formation. So let us now discuss about the nuclear stopping. Some of the ions impinging on a semiconductor conductor surface are reflected by collision with the outermost layers of atoms. Some impart sufficient energy to target atoms, which are then ejected from the substrate by a process known as sputtering. So in this section, our interest focusing on the nuclear stopping process, where the majority of the incident ions penetrate into the semiconductor and transfer their energy to the lattice atoms by elastic collisions. Detailed calculations for nuclear stopping were first advanced by Linhart, Schroff and Scheidt LSS and are available in the literature. So here the approach used in developing them is outlined in order to gain some insight into the implantation process. Consider an elastic collision of two hard spheres, each of radius r0 as shown in this figure. Let nu0 and e0 be the velocity and the kinetic energy of the moving sphere projectile of mass capital M1. The mass of the stationary sphere or target is capital M2. After collision, its velocity and kinetic energy becomes nu2 and e2 respectively. So in like manner, let nu1 and e1 be the velocity and kinetic energy of the projectile after impact. So the distance between the spheres is given by an impact parameter p. For this model, energy transfer only occurs if p is less than equal to 2r0. A head-on collision is represented by p equal to 0. Upon collision, momentum is transferred along the line of centers of the sphere. In addition, the kinetic energy is conserved over here. So if we solve for these conditions, the projectile deflects from its original trajectory by an angle theta, such that cos theta is equal to half multiplied by 1 plus m2 by m1 multiplied by root of e2 by e0 plus 1 minus m2 by m1 multiplied by e0 by e2 ka square root. This is whole multiplied by half. So this equation shows that the energy transferred to the target particle is related to the scattering angle theta. In addition, the velocity nu1 of the projectile after impact is given by nu1 square equal to nu0 square multiplied by, in the numerator we have m1 cos theta plus m2 square minus m1 square sin square theta, the square root of it, divided by m1 plus m2. So maximum energy is lost by the projectile in the head-on collision with the target particle that is initially at rest. So for this case, the final velocity of the target m2 is nu2 equal to 2m1 by m1 plus m2 multiplied by nu0, so that the energy gained by it is Tm, which is given by Tm equal to half m2 nu2 square equal to 4 m1 m2 divided by m1 plus m2 the whole square multiplied by E0. This is also the energy which is lost by the projectile m2. The situation is more complex when the projectile and the target have an attractive or repulsive force between them. Associated with this force is a potential VR, which usually extends out to infinity. If this is the case, both particles will be continually moving without physical encounter as they approach each other, as shown in this figure, so that the impact parameter also extends out to infinity. So the energy transferred in this process is thus somewhat less than Tm and depends on the impact parameter. The problem now reduces to a system of point masses moving under the influence of this potential and has been classically treated by two-particle elastic scattering theory. Now here the approach consists of transforming from laboratory coordinates to a set of moving coordinates whose center is located at the center of mass of the system. So this renders the problem symmetric as shown in this figure, with a deflection angle phi between the particles, which is given by phi equal to pi minus 2p multiplied by integral minus infinity to Rm over dr by r square multiplied by 1 minus Vr by Er minus p square by r square to the power 1 by 2, where p is the impact parameter, Rm is the minimum distance of separation between the particles, and Vr is the interaction potential function. Now students, the Er, which is the energy of the ion in the center of mass system, is given by Er equal to half multiplied by m1 m2 by m1 plus m2 multiplied by nu0 square. So now students, integrating the above equation for theta can be evaluated for any given interaction potential function. So the magnitude of theta in laboratory coordinates can be shown to be given by tan theta equal to sin phi by cos phi plus m1 by m2. And the energy transferred by this process is given by Tn as a function of E and P equal to E naught multiplied by 2 m1 m2 by m1 plus m2 the whole square multiplied by 1 minus cos phi. So the choice of VR is based on physical consideration of what happens if two atoms with atomic numbers Z1 and Z2 approach each other at a distance r. So the force between these atoms is Coulombic in nature and is given by Fr equal to Q square Z1 Z2 by R square, and the corresponding potential is given by Vr equal to Q square Z1 Z2 by R. This situation holds only as long as the electrons of each atom are excluded. So their inclusion, however, results in a screening influence on the nuclear repulsion, which causes a modification of the potential function. So one general form of such a potential function is Vr equal to Q square Z1 Z2 by R, F as a function of R by A, where A is the screening parameter and F as a function of R by A is known as a screening function. So one such function, which is shown in this figure, is known as a Thomas Fermi screening function and has found to be useful in the calculations of nuclear stopping power. Often it is approximated by A by R, where A equal to 0.885 A naught by root of Z1 to the power 2 by 3 plus Z2 to the power 2 by 3. And A naught is the Bohr radius, which is around 0.53 angstrom. So for this approximation, the potential is inversely proportional to the square of the distance. So using either the Thomas Fermi screening function or its approximation, the deflection angle phi and hence theta can be computed for any impact parameter P. So this in return allows the computation of TNEP, the energy lost by the incident particle in an elastic encounter with a single stationary particle. In the practical situation of an amorphous target of thickness delta x and having an atom density of n, energy is transferred to all the particles and the total energy transferred is obtained by integrating over all possible values of impact parameter so that delta E equal to minus n multiplied by delta x integral 0 to infinity TNEP multiplied by 2 pi p dp. So the nuclear stopping power is thus given by SNE equal to integral 0 to infinity TNEP 2 pi p dp. So students, using this approach and Thomas screening function, the relationship for nuclear stopping power takes this form. Now here we note that as the ion enters the semiconductor, that is for large values of E, it first transfers energy to the lattice at a relatively slow rate. So as the ion slows down, this rate of energy transfer increases and then eventually decreases to zero as the ion finally comes to rest. So use of the approximate form of the screening function, where the potential is inversely proportional to the square of the distance, leads to a constant rate of the energy loss, which is shown by the dashed line in this figure. So the approximate expression for this rate of energy loss turns out to be minus dE by dxn is approximately equal to 2.8 multiplied by 10 to the power minus 15 n multiplied by z1 z2 by z to the power 1 by 3 multiplied by m1 by m1 plus m2 electron volt per centimeter square, where z to the power 1 by 3 equal to z1 to the power 2 by 3 plus z2 to the power 2 by 3 to the power half. So this corresponds to the energy loss rate of about 10 to 200 electron volt per Armstrong for most ion target combinations. So students, let us now discuss about the electronic stopping, a comprehensive treatment of inelastic energy exchange process which accompany the excitation and ionization of electrons by collisions with incident ions can only be provided by a quantum mechanical approach. However, semi-classical approaches can give reasonable estimates for the energy loss rate due to these processes. So the fact that electron excitation and ionization do indeed occur is really seen by considering the head-on elastic collision between an ion of mass m1 having energy E0 with an electron of mass m2, that is small m0. So since m1 is very much higher than m0, the maximum energy transfer due to this process is given by 4m1 m0 divided by capital M1 plus small m0 the whole square multiplied by E0 equal to 4 small m0 by capital M1 multiplied by E1, E0. So the excitation energies are a few electron volts, where capital M1 by small m0 is varying from 1000 to 2000. Consequently, both electron excitation and ionization are possible since the energy of incident ions during implantation is normally in the range of 50 to 500 kilo electron volts. Approximate computations of the inelastic energy loss rate associated with this process have been made by considering the projectile and target atoms as forming a quasi-molecule with energy transferred due to electronic interaction as the particles undergo an encounter. As before, the total energy transferred to a target of thickness delta x can be obtained by integrating over all values of the impact parameter, so that delta E equal to minus n delta x multiplied by integral 0 to infinity Te as a function of E and P multiplied by 2 pi p dp, and SEE equal to integral 0 to infinity TeEP multiplied by 2 pi p dp. So the rate of energy loss can be shown to be given by minus d by dx E is approximately equal to 2.34 multiplied by 10 to the power minus 23 n multiplied by z1 plus z2 nu naught eV per centimeter square. So the projectile velocity is given by nu naught equal to 1.412 multiplied by 10 to the power 6 multiplied by E naught by m1 to the power 1 by 2 centimeter per second. So that SE is approximately equal to 3.3 multiplied by 10 to the power minus 17 multiplied by z1 plus z2 divided by m1 to the power 1 by 2 multiplied by E0 to the power 1 by 2 eV centimeter square. Thus, the rate of energy loss due to electronic stopping is several 15 to 50 electron volts per Armstrong, which is somewhat less than the energy loss rate for nuclear stopping. So students, let us summarize what we have learned in this module. First, the characteristics of ion implantations were discussed. Second, the expression for penetration range was discussed and derived. Thirdly, the nuclear and electronic stopping phenomena were discussed in detail. Thank you.